disproportionation reactions. Okay, and the RxN obviously stands for the reactions, and we'll also look at a redox table later on in this video. Let's have a look at what these things are. First up, a disproportionation reaction is when atoms of an element undergo oxidation. And you should be comfortable with oxidation, right? The loss of electrons. But sometimes atoms of that same element can also undergo reduction. And this is very odd because so far we've been looking at a particular element doing oxidation and another element doing the reduction, okay? But in a disproportionation reaction, that same element undergoes oxidation and that very same element undergoes reduction. Let's have a look at an example. As you can see here in this example, we have a balanced, and this looks like an ionic equation. Okay, EQ stands for equation, but whenever we want to figure out disproportionation, like what we've been doing in the previous videos, we've been doing half reactions. We're going to make this into a half reaction, okay? But before we do that, it would obviously be beneficial to create a net ionic equation first. And then we cancel out all of the like terms within this equation so that we can figure out what are the spectator ions, the one that doesn't do any of the, the transfer and the receiving of electrons, the useless ones, okay? They're just spectating. And then whatever's left over, then we can start creating a half reaction, okay? So let's just first start off with this one here. So we have our Cu2O, and this can obviously be broken down because it is an aqueous, right? We just can't do that for our solids. So for our Cu2O, obviously, this 2 came from up here, it crossed over, so this was just a 2 minus, and this 1 over here, that invisible 1, must have come from up there, okay? So the original charges for the Cu was 1 plus, okay? But we see that there are 2 of them, okay? So I'm just going to be putting a 2 in front of there, and as again, oxygen has a 2 minus charge that we just established, okay? And there's only 1 of them right now, okay? So let's just put that there. And then again, for the H2SO4, hydrogen always used to have a charge of 1 plus, and whenever we deal with polyatomic ions, you should already know this by now, right? We always leave the brackets around the polyatomics and the charges on the outside. So if hydrogen was on its own and SO4 was on its own, because obviously SO4, it's on your periodic table, it's sulfate, it's a polyatomic ion, okay? That 2 minus goes down over here, and there's where that 2 is, okay? And this 1 plus goes down here, and that's where that 1 is, okay? So if I were to put that bracket within the actual compound up here, technically it would look like that, okay? There's an invisible 1 on the bottom, okay? But obviously this compound just looks like H2SO4, okay? Just straight through, but technically that H2SO4, okay, this thing over here is literally this, H2SO4 together in brackets and a 1 on the outside. So H plus has that 1 charge, and there is 2 of them, we can't forget that. And SO4, 2 minus, we've already established it's a polyatomic ion, has a 2 minus charge. There's only 1 of them, so I'll just put that 1 over there. And what is it going to yield? Nothing changes for a CuS, it is a solid. And this one can break apart. Again, SO4, 2 minus, right? That was its original charge, so that 2 minus must have gone down there, okay? And this Cu, okay, what was its original charge? It must have been a 2, because that 2 must have went down all the way there, okay? So if that's the case, we have 2 and 2 on the bottom, so this kind of goes away, this kind of goes away, all right? What must have happened, okay, in order to give us a clean CuSO4, okay? Why is there no numbers on the bottom? It's because this 2 divided by 2 and this 2 divided by 2 to get the smallest, whole number, which would have become a 1, right? So then this goes away and this goes away, and you get a 1 over there and a 1 on the outside. Okay, there's obviously a bracket. in between, okay? So the charges were obviously 2 plus for the Cu and 2 minus for the SO4. And again, there's just one copper and there's just one SO4, so you can put those in front if you wish. Okay, we can just keep it invisible, and H2O, nothing happens, it's a liquid. Okay, it's not aqueous. So what can we do to cancel stuff out? Obviously we have one SO4 here, one SO4 here, so that's gone. So now everything else, I believe you need to keep. So let's just continue to write this down, make it a little bit more clean. Okay, so we've done that. However, I do want to only focus and revolve around disproportionation, okay? What's so special about that? So if we were to break it up into its half reactions, but revolving only around these coppers, let me show you something cool. Well, technically, in this little box over here that I want to outline, there are two coppers, right? So this Cu 1 plus, okay, there's one of that, okay, there's a 1 in front, but there's also technically another copper 1 plus, okay, because two of these make up that 2 Cu. And then on here, on this side, okay, the two coppers that we have here is one that has an oxidation number of 0 and one here that has an oxidation number of 2. So if we were to look at these two Cu1 pluses, let's say this one goes to this copper and this one goes to this copper. Well, that had a oxidation number here of 1, right? It went down to 0, so it reduced down to 0. So this here would be reduction. Okay, this means that there was a gain of an electron. Okay, gain 1 electron. However, this one, okay, this 1 plus went to this 2 plus. Obviously, it went up in oxidation number, which is oxidation. Okay, which means it lost 1 electron. Okay, so as you can see, this 2Cu1 plus, which is embodied here, what happened? There was a gain of 1 electron right over there, and there was another transfer, so oxidation, a removal, a loss of an electron happening over here within the same element. Alright, so now let's look at this table here. It is revolving around this topic here, the redox table. The check marks indicate the reaction between the metal and ion in solution that was spontaneous. So as you can see, these ions on the top are going to be cross-examined with the metal atoms here on the side. So if this Ag plus, right, the silver cation reacts with a Cu, and that Cu was within a compound, what's going to happen? Is this Ag plus going to kick the Cu away and displace it? Absolutely. That's what the check represents. Okay, same thing with Ag plus and Zn, or Ag plus and Pb, or Ag plus and Mg. As you can see, Ag plus is extremely powerful. It's going to kick them out and displace it, and then this Ag will then become part of the compound, and then these ones will just kind of be kicked out on their own now. But we have an example of here where we have a Cu2 plus, okay, if it encounters an Ag within another compound, can this Cu2 plus kick out the Ag? No, it cannot. As you can see, there are these dashed line symbols that represents that it's not strong enough to do that. We actually looked at this question. See the video link in the description about spontaneity. We had a video revolving around this topic. I kind of want to bring it up again. Which of the 3 solid metals, when placed in the aqueous solution of cadmium chloride, will react spontaneously? Well, in that video, we had a look at this chart where we had CdCl2 as the aqueous compound, and we had to find the metal that displaces it, right? So as you can see, we have Cd over here, and we, in that video, looked at which metals can displace it, and it was all of these ones below it, okay? Any of the metals that are a stronger reducing agent that are on their own, right? So let's say, I think we used CR in that video, okay? And the CR revolves around a charge of 3. It is a multivalent, okay, ion, but in this case we're using the 3 plus charge. Okay, if this one here was alone, okay, on its own, so let's say we have CRS here on its own, again we know that its charge was a 3 plus up there. If this was alone on its own and it reacted with our CdCl2, because this CR is below the CD, okay, so it is a stronger reducing agent, it will absolutely kick it out. Okay, so it's going to come here, kick out the CD, and now the CD is going to be on its own. All right, so let's show how. So we have our CR, we know that it has a charge of 3 plus, and if it reacts with this CD Cl2 that I just showed you, what's going to happen? Again, CR, we knew that it has a charge of 3 up there, right? And it's pretty obvious that CD has a charge of 2 based on where the subscript is, okay? So let's have CR and Cl together. So obviously 3 is down there. Cl has a -1 charge, so obviously that's down there, invisible. And then now the CD is kind of on its own, okay? Again, this should be an aqueous, so obviously this is now an aqueous, okay? So let's break it apart and prove that this yielding of product works out, that there is displacement, that the CR does deserve to kick out that CD. So again, we have a CD has a charge of 2 plus. Okay, there's only one of them, so I'll just put a 1 over there. It's still aqueous. And Cl has a charge of -1. Okay, again, there's 2 of them, so I'll just put a 2 there. This is all aqueous. Okay, it's yielding. Cr, okay, so we know that Cr has a charge of 3 plus. Okay, this is also aqueous. There's only one of them right now, and this Cl over here has a -1 charge. Again, there's 3 of them though. This is all aqueous, and then the CDS, nothing changes, it is a solid. So can we cancel out any like terms? Unfortunately, we cannot, but let's look at the oxidation numbers, okay? So again, we have an oxidation number up there of 0 for the chromium. Where is the other chromium on the other side? It's a 3 plus, which means it has an oxidation number of 3. Okay, so I'll put a 3 up here. This one was a 0. Okay, so let's look at these two things together. Okay, so obviously this is oxidation. Okay, it went up in oxidation number from 0 to a 3, so this lost 3 electrons. All right, and then what else do we have? Okay, Cl minus, they're both a -1 charge, so their oxidation numbers are just a -1, so nothing really changes, so we don't have to look at that. But this has an oxidation number of 2, and this has an oxidation number of 0. Okay, so let's bring this down here and examine it. Okay, so we have 2 went down to a 0, so it obviously got reduced. Okay, and it obviously gained 2 electrons. So if this here was oxidation, okay, it got oxidized, that means this here is the oxidizing agent. And if this one here is being reduced, right, as we've listed down there, it's reduced, that means this one here is the reducing agent. Now, here's the rule, okay? As long as the oxidizing agent is stronger than the reducing agent, there will be a spontaneity, okay? There will be spontaneous reaction, okay? So let's look at this CD2+. If it's stronger than its corresponding chromium. As you can see, CD2+ on this table is above the chromium. So this oxidizing agent is above that reducing agent, so there will be spontaneous reaction. So therefore, this would be a spontaneous reaction. So going back to this question after that little spiel, okay, let's have a look at A, okay? Which aqueous ion is the strongest oxidizing agent in this group? So let's have strongest up here, and we can have weakest down here. Obviously, it is the Ag+, because it has so many check marks. It can displace this guy, this guy, this guy, and this guy, all right? So the strongest is definitely the Ag+. What else is stronger after that? Obviously, the Cu2+. Okay, it can displace this guy, and this guy. So we have Cu2+. just before that. What's after? We have the PB2 plus, because it has 2 check marks as opposed to just the 1 from the zinc. And the Zn would be after that. And let's not forget about the Mg2 plus. Can't displace anybody, so that's at the bottom. For B, we've kind of already did it. Okay, it's asking for the weakest oxidizing agent, so it's obviously this one down here. We've already pretty much answered it for A. Okay, so B is kind of finished over there. And for C, we have to create the half reaction. Okay, so we're going to make the Ag. Okay, in order for them to balance out in terms of charges, we have to add 1 electron here, because this 1 minus 1 gives that 0, just like how Ag has a 0, okay? For the Cu2 plus, in order for it to become a Cu atom, this is a 2 plus, you're going to add 2 minus, which is the electrons, that'll give you that balanced. For the Pb2 plus, again, for it to become the Pb atom, same thing, add 2 electrons, 2 minus 2. For the Zn, same thing, add 2 electrons, 2 minus 2, and same thing for the Mg. For it to become the Mg, just plus 2 electrons, okay, 2 minus 2. Alright, so let's try this question over here. Now it's also saying to organize the half reactions from the strongest to weakest, but we are now looking at table 2, right? We are expanding that table a little bit. So let's answer that question down here on the bottom. We have the strongest on the top and the weakest on the bottom. Pretty obvious, this Ag plus is going to be having 3 check marks, so it is the strongest again. What else do we have? Then we have the Pb after that. And then we have the Sn2 plus. And then lastly, the Zn2 plus, okay? So I've already written down here what we had in our result from table 1 in the previous question. Okay, so Ag and Ag, they're common over there. Cu2 plus, oh, Cu is not over here, interesting. Okay, Pb2 plus, it's over there. Zn2 plus is over there. Mg plus, oh, it's not over here, interesting. Okay, so there's 2 that are not there on this side over here. Okay, so let's see why. So the question after that says, place the 6 different half reactions in one larger table, placing the strongest oxidizing agent at the top and the weakest at the bottom. Okay, so I'm just going to split this up a little bit. And why do they say 6 different half reactions? Let me show you. So again, we have strongest on the top and weakest on the bottom. Ag plus seems to be the strongest. Okay, so let's get rid of this Ag plus, let's get rid of that Ag plus. What else do we have after that? We have the Pb2 plus and this Pb2 plus. Okay, however, are we sure? Are we going to really rule out that this Pb2 plus and this Pb2 plus are going to be the second one? Or are we going to be putting the Cu2 plus over here before this Pb and Pb? Well, as you can see in this table, right, table number 1, this Cu2 plus, if paired with a Pb in a compound, as you can see, it can absolutely displace it, which means the Cu2 plus is actually stronger than the Pb. So we can put this Cu2 plus, we can cross it off. It's not here on this side, so that's fine, but we have to add it this as the second strongest, okay? Then we can add our Pb2 pluses. Okay, so now this one and this one is gone. What else do we have? Okay, Zn seems to be the stronger one after that, but we have a Sn2 plus that is trying to contest as becoming the next one in line, okay? So how do we solve this? Same thing. This time we'll be looking at table number 2. Okay, so there's Sn2 plus and this Zn. Look what happens when the Sn2 plus encounters the Zn within a compound. It absolutely displaces it. Okay, it kicks it out. So this Sn2 plus is going to be stronger. Okay, so we're going to ignore this one over here. We're going to be putting the Sn2 plus first. Okay, so let's cross that out and put it next in line. Then we have our Zn's, and then we have our Mg's at the very end. It can't displace anybody, as referred to in table number 1. And we don't even see Mg here in table number 2 at all. So this seems like a pretty good list. And as you can see, if you count it out, 1, 2, 3, 4, 5, 6. Okay, exactly what was written in the question, the 6 different half reactions. Please try this question on your own. I know it says in the tables above, right? But that's technically below. Okay, so the table, the only table that you should be referring to is this one over here. Okay, determine the relative position of the metal versus the ion and determine the spontaneity. Okay, so just write down in here, and here, and here, and here, the relative position. Okay, again, the first one below has been done for you, so this one. Okay, so is the oxidizing agent below the reducing agent, or is it the opposite? Is the oxidizing agent above the reducing agent? Okay, and then also tell me whether in these boxes whether they're going to be a spontaneous reaction or not. This is the answer to the first question. I will slowly scroll down.